Hello, and welcome to another introduction to quantitative analysis. We had a similar module earlier in the class in which I gave you a very high-level overview. And in this portion, we'll be going into some of the same topics and questions, but a little bit more in depth. So first, quantitative analysis is descriptive statistics, comparisons, and relationships. And this is what we'll be briefly discussing today: descriptive or summary statistics, t-tests, correlations, ANOVAs, and chi-squares. This should all look at least relatively familiar to you because, again, we covered it in an earlier block in this class. So just a very quick refresher of what descriptive statistics, or sometimes they're called summary statistics, are: the mean, which is the average; the median, which is the exact middle point of your scores or of your data; the mode, which is the most frequent number in your data; and the range, which of course is between the high and the lowest points in your data. Remember the importance of including both percents or proportions as well as counts, and how that can be helpful in telling a more full story of your data and using your data to really show the picture of what is happening. And then also, in the next slide, I'll present a real life example of how it's important to present the most appropriate descriptive statistic and how mean and mode can get at a different sort of result, if you will. So this table is a table from a report by Bracco, Barrett, and Finkelstein from this past year. And this has to do with, I think, what I have possibly already mentioned in this class is my work on a developmental education reform in the Cal State system for undergraduate introductory level courses. And what you can see here is the placement category is that first far left column, and you can read the different levels of placement into math. Math is that GE sub area B4 course. And what I want to point out is we are looking at here the number of credits students attempt in their first academic year in 2018 to 2019. And if you look at the column that is the mean, you can see that that first row, or the students who come into the CSU having already completed that math requirement, so most likely they took a fourth year of math in high school, maybe they have already taken calculus, or perhaps they've tested out of it with an AP score, that sort of thing. If you look at the mean number of credits that students in that category attempt, it is 28.3. From a policy perspective, we would like each student to be attempting at least 15 credits per semester. That would be 30 per year to keep on track for a baccalaureate degree of 120 units. So in general, these placement categories are: category 1 is you have already completed the requirement, and category 4 is you're really entering the university needing a substantial amount of support. So if you look back to the column that describes the mean, you can see that as the placement category increases in number, again from 1 to 4, those are students who actually have a decreasing level of academic preparation. And you might expect that those students in categories 3 and 4 who are needing a little bit more academic support are attempting fewer units, right? Maybe they are concerned about adjusting to the university, the rigor of the courses, that sort of thing. However, we see that students in all 4 placement categories are actually taking fewer than 30 units on average. Then I want you to look at the mode column, which is 2 columns to the right of the mean. And I want you to look at placements category 1 and 2. And what the mode is telling us is that actually that is the most frequent number of credits that students in these categories are attempting, 30, and that's exactly where we want them to be. You can see that students in categories 3 and 4 are attempting 27 units respectively. And even though that is lower than what we would hope, again, the the number of credits that students are taking most frequently, right, is 27. And that's higher than the average of 25.8 for those category 4 students, for example. So, whereas it looks like they're taking less than 26 credits on average, that's true. However, most students in category four are taking 27 units. And so that's a slightly better picture than we might get if we only report the mean or the average. Okay, so now we're going to go into t-tests. And t-tests basically ask the question, is there a statistically significant difference between two groups? And this is two groups on a continuous measure, so a very easy example to use is test scores, and I'll be using test scores throughout this PowerPoint as the example. There are several different types of t-tests that you can conduct. One is a typical treatment versus control group. So one group gets a reading intervention, one does not. And this is an independent samples t-test. Pre and post test are paired sample t-tests because they are the same participant. The same participant has paired scores, one from the pre-test, one from the post-test. And then there's the sample and population comparison, where you have one test of scores, say your own classroom, and you are comparing it to a nationally known average score, again, for example. So if we are wondering the question, how do students' exam scores compare with the new diversity, equity, and inclusion reading program, we actually need to ask another question to figure out what exactly we're trying to look at. So, are we comparing the same group of students who use the old and new curriculum? Are we comparing two groups of students, say from two different classrooms? Or are we comparing one classroom again to a known number, like a national average reading test scores? So those are actually all three different questions and all three different t-tests, as I just described. I'm going through this rather quickly because, again, this was covered in the earlier module, but in the next slide, we'll go into some calculations. So again, here is a t-test where we are comparing two different groups of students, one group who used the old curriculum and one group who used the new curriculum. And this is just in one time period. Here is the equation for calculating this. And I gave you a really, what I think is a really great resource for t-tests and calculations, that website. You can actually just enter data right into the website and it'll calculate it for you. But in short, the X bar, which is on the very top, that is the mean. And X bar sub 1 and X bar sub 2 are the means, again, for those two different groups. We basically have a treatment and control group here. And then N is, of course, the size of the sample. And whereas we will not be calculating this by hand, in this slide, I show you the computer's calculations. And you can see that on the left side, you can see all those different calculations for treatment 1, all those different calculations for treatment 2. And the most, what I find the most important or the most intuitive to understand is the means. So if you're looking at treatment 1 and you're looking at the M sub 1 number, it is 14.58. So that's the average score that students in the treatment 1 group got. Same for treatment 2. M sub 2 is the average score of 13.85 for students in that group. The computer has then calculated the t statistic, and you can see that it equals 1.27. The computer also calculates a p-value, which tells you whether or not it's significant. And using the standard p-value of 0.05, we can see that the t-value is 1.2, 6669. The p-value is calculated at 0.21, which actually isn't shown in the calculation just due to my cut and paste. But the result is not significant, again, because that p-value is not less than 0.05. So a way that you can write this as a finding is the 12 participants who received the new reading program, who have a mean of 14.58 and a standard deviation of 32.27, compared to the 13 participants in the control classroom again, include those statistics, demonstrated similar reading test scores. And they're similar because, again, we do not have a p-value of less than 0.05. And there's two different ways to write that. You can either report the actual p-value, so in this case, p equals 0.22, or you can just say p is less than with that kind of sideways caret, 0.05. So again, this was the t-test comparing two different groups of students. And this is the t-test and formula for comparing the same group of students who used the different curriculum in different time periods, right? So we're really looking at time 1 versus time 2 here. And again, here's that formula, and here are the output that you get by the computer. Again, you can see that the mean difference between the first and second test is 1.59. That's what that mean means in this type of calculation. And then when you're calculating the t statistic, you can it is 4.94. So again, the computer calculates a p-value, and in this case, the result is significant. So a way that you can write this up in a findings section is students' reading test scores increased by an average of 1.59 points after the new diversity, equity, and inclusion program was introduced. And then at the end of the sentence, you include that number in parentheses. That 17, that's the number of participants we had. That's the number of data points, the number of students in the classroom. So T for 17 students equals 4.94, and that is significant because it is at a p-value of less than 0.05. The third type of t-test is that where you compare your score or your average scores of your classroom to a known value. Here is the formula for this. And in general, a t-score indicates a significant difference. A large t-score indicates a significant difference, and a small t-score indicates more similarities between groups. And you should have been able to see that in the last two examples. One was a smaller t-statistic, it was, or a t-score, it was on the smaller side, and that example was not significant. Again, those test scores were similar to each other. The larger t-score indicated a significant difference between groups. And here again, we see that the finding in this outcome in this example, comparing test score to a known score, the t-value was negative, meaning that it is lower, but the result is significant because the p-value was less than 0.05. In this formula, M is the average score for your test score, and mu, that's that fancy U looking example or letter, is the known average test score, again, that national score that we're looking at here. Of course, X is the average there. Nope, sorry. The X's under the bar there are the individual scores. So you need the sum of the scores squared. And the rest of that is the N, of course, is the number of students again. Okay, so moving on to correlations. Again, this should be a little bit of a refresher. You can see here that image number 1, that's a pretty tight positive correlation. Image number 2 is still positive, a less strong correlation. And image number 3 is no correlation at all. A positive correlation indicates a positive relationship, so that when the first variable X increases, Y also increases. And that is also true for negative correlations. So when X for decreases, right? So it's still a positive correlation if X and Y decreases together in the same direction at the same time. A negative correlation indicates a negative relationship when one variable increases and the other decreases. and they're going in the opposite direction. And correlations are you get a value that range from -1 to 0 and 0 to 1. So this is the formula for correlations. And again, that handy little website I have there, these are the values that I input for a sample. And you can see that it's plotted here. So if you look at this bottom blue dot here, these ones, you can see a positive line here. These are lower values on X and lower values on Y. This is not officially an outlier, but a little bit of an outlier compared to the rest of the trend. And then you can see a positive direction here, higher values on X and higher values on Y as well. So this is the output that the calculator gives you. And what I've circled there is the R value. So we know that this is a positive correlation correlated at approaching the 0.8 level, which is a relatively high correlation. 0.8 and above is high. So we can see here that it's a positive correlation based on this output. And it is a p-value that has also been calculated, not shown here, but it is a p-value less than 0.05. So it is a significant correlation. I recommend you kind of pause here and take a look at what the key is in all of these calculations. You're not expected to do them by hand at this point, but you can see that there are the X values. Of course, those are the values for the X variable. The Y value is for the Y variable. And there you go. So now we're moving on to ANOVA, or analysis of variance. ANOVA determines significant differences across more than two group means. So t-tests really are only used when you have two different groups, and ANOVA can be used when you have more than two groups. So that's really the purpose, or when you have different levels, right? So if I want to compare across 3 classrooms, each classroom is considered a level. And so that is when we can use an analysis of variance. The analysis of variance tells you, the output will tell you if there is a difference between the groups, but it doesn't indicate which groups are actually different from each other. So again, thinking about 3 different classrooms, it will say there is a significant difference, but by that output alone, you don't know if it's the difference between classroom 1 and 2, class 3, or between classroom 1 and 3. So that's why you would run an ad hoc test. So here is some output from a one-way ANOVA. We are interested in here, you're calculating the between treatment differences and also the within treatment differences. So I like to look at the column, not the far right column, but the second to the right column, and think about how that makes sense. The between treatments average differences, right, are going to be a lot larger than the within treatments. You would expect students within the same classroom to possibly have closer scores, especially if you're thinking about different levels of treatment, right? So if classroom 1 has an outdated curriculum, classroom 2 has the new equity and justice reading program, and then classroom 3 has the new reading program with additional tutoring, right? Those different levels might have a big difference. And so that's why the between treatment differences are a lot larger than the within treatment differences. So this is the output, and then you're given that F statistic. And that F statistic is significant. There we go. That F ratio is significant, and but it does not tell us, again, which of those 3 different comparisons are different from each other. Is it the old school curriculum is different from the new curriculum? Is it the new curriculum is different from the new curriculum plus extra tutoring? Or is it that the the old school curriculum is different from the new curriculum with tutoring. And here we can see that there are two significant differences. The first one, the first level of comparison is treatment one to treatment two, or classroom one to classroom two. In this case, the original curriculum to the new curriculum. That is not significantly different. Then we see treatment one compared to treatment two, or I'm sorry, treatment three. In this case, the old curriculum compared to the new curriculum with tutoring, which is significantly different. And that's what we would expect, right? It's new and it's got an added component. And then we see that there is a significant difference between the new curriculum and the new curriculum with tutoring. That might be expected, it might not be expected, but in this example, we do see that those are significant. And we know that because of the p-value right here, both of these are less than 0.05. So again, this is the ad hoc test that you get after computing the actual one-way ANOVA itself. This is a one-way ANOVA with repeated measures, and you get a very similar outcome or output, right? But in this case, it's just the same participants, right? So again, we're looking at a classroom that has taken the test multiple times, and then we're comparing those different test scores. So here we have the F ratio of about 21, and this of course is significant because the p-value is less than 0.05. There's also a two-way ANOVA, which has two independent variables with two or more levels, right? So in this example, we have the mean test scores across 3 different classrooms or 3 different teachers, right? We just discussed that example. And then also whether or not the classroom, this subject takes place before or after recess, right? So that's our second independent variable. The first independent variable is the classroom or the teacher. The second is the time before or after recess. And of course, the dependent variable is the mean scores, the mean reading scores. So here is an example of some output here. And in this case, we see we're actually looking at multiple comparisons. So this time we're not only comparing old school treatment with the new treatment, the old school treatment with the new treatment plus tutoring, and the new treatment compared to the new treatment plus tutoring. That would be the that first row across, that's the teacher comparison. But we are also looking at whether or not time has a difference, right, before or after recess. So we can see that both of those factors do have a significant impact on test scores, right? And we see that by the F value that is there for the different classrooms or the teachers, which is right about 9.1, and that is less than 0.05. And then we also see that the time before and after recess is a significant factor in test scores, with that F value of being more than 15 and that p value being less than 0.05. Okay, next we have chi-squares, and this is a significant test to compare frequencies or counts with observed and expected ratio, or observed and expected scenarios. So what that means is if it is an expected scenario, right, every person has the same chance of doing something. And the important thing to remember with chi-squares compared to any of the other things that we've been looking at is that these are not continuous. These are not test scores, right? These are categorical variables, which means they're non-numerical. There's no number associated with your gender. There's no number associated with your race. And there's no number associated with, yes, you did or did not participate in after school sports. You participated in basketball or track, right? Those are all categories, not numbers. So here we're wondering if there's a difference between genders and who participated in sports. And in the example, I actually knocked out soccer, so it's just basketball and track. And here is our formula. And again, we're looking at observed and expected outcomes. And so that's what the O and the E are in the formula. And those fancy looking E's, those just mean sum, right? Um, so the results indicate here that there is a significant relationship between gender and which sport students play. Our chi-square is 29.48, and it is at the less than, P is less than 0.05. And in general, a larger chi-square indicates a larger discrepancy between the observed and expected values. So what that means is, if you look at the table that I've provided, 70 boys play basketball and 40 girls play basketball. And what's presented in the parentheses is what you would expect. You would expect roughly 50 boys to play and roughly 60 girls to play. And then we can see a similar style or formula for the output for track, right? 31 boys actually participate in track, assuming no relationship between gender and sport. You would assume about 51 boys run track. And assuming no relationship between gender and sports, you would assume that about 62 girls play track when actually, or run track, when actually 81 girls run track. So what this chi-square statistic of 29 is saying is that there is a significant difference between what we are expecting to see, again, those numbers in parentheses, and what we actually see playing out at the school. So that's how to interpret this table. There is a significant relationship between gender and sports choice. And you can see that, right, based on the numbers. We can see that girls, many more of them run track than boys. We can see many more girls run track than play basketball, right? So in general, this outcome or this conclusion that there is a significant relationship between gender and sport, it makes sense once you really look at the data, and it becomes somewhat intuitive. Again, looking at basketball, we have more boys that play basketball than girls. Just, 70 is fundamentally higher than 40. We also have more boys that play basketball than track. But we also have more boys that play basketball than expected, right? Again, that's 70 versus about 50 in that parentheses. So again, the chi-square is really comparing what you have observed in real life at your school with what you would expect if there were no relationship between the two variables. So that's how you should be thinking about chi-squares. Okay, any of these calculations may or may not fit your quantitative analyses, right? You need to be thinking about your research questions and which analysis really helps you answer them. Which types of data are you looking at? Are you looking at numerical data? Are you looking at categorical data? Are you comparing across time? Are you comparing the same group of students at 2 time points? Are you comparing different groups of students so that it's an independent sample? Those are all things that you'll need to consider as you work through your quantitative data analysis. Thanks and good luck.